Hello everyone, welcome to OdinSchool. In this class, we are going to learn about few of the very important aspects and components in statistics. We are going to learn about confidence intervals. We are also going to learn about level of significance, and then we will learn about degree of freedom as well. So all these components are very vital and comes into picture when we are dealing with hypothesis testing. Hypothesis testing is one of the most widely used statistical technique or a concept in both descriptive and predictive analysis. So it is important to know all these components of hypothesis testing, which will help you to understand how hypothesis testing can be interpreted. Now, before getting into the content, let's first understand why do we need statistics. Statistics is one of the most widely used subject both professionally as well as personally. Even in our personal life, if we have to take a decision, we will always try to go with a quantitative analysis. Say for an example, I wanted to go to a particular location at a particular time. I will have to start my vehicle. I have to start leaving my place like 30 minutes before the function begins, or considering the traffic I'll have to leave 45 minutes begin. So every small decisions and the bigger decisions that we take in life is basically calculated in the form of numbers. All this numerical calculations gets into shape when you apply statistical measures on top of it. Basics, to give an example, we calculate average salary that we are earning. We will calculate the loss that we incurred over a period of time. All those basic calculation are supported by statistics. So knowing statistics does not only help you professionally, it also helps you personally. With that said, let's quickly introduce about OdinSchool as well as about me. OdinSchool is a technology upskilling platform. They help us continuously acquire new skills. Their motto is to stay skilled and stay ahead. About me, I'm Gautam Kumar Jayachandran. I have 6+ years of experience as a senior data scientist. I work in several technologies like Excel, SQL, Python, Tableau, machine learning analytics. Currently, I work in the financial domain. Now let's understand what is today's agenda. As I said in the beginning, we are going to learn about confidence intervals. We are going to learn about levels of significance, which is also called as alpha levels. Then we are going to learn about p-value. Finally, we will learn about degree of freedom. So we will see all these concepts with examples. First, theoretically, confidence levels. Confidence intervals is basically a type of estimate calculated from the statistics of the observed data to incur the level of assurance to hypothesis. So what is the insisted keyword here is the assurance to hypothesis. I'll explain this with an example in a very layman's term. It proposes a range of possible values for an unknown parameter. Confidence interval has been associated confidence interval that the true parameter is in the proposed range. If you see this distribution, this looks like a normally distributed data where there is a limit of 2.92 in the left side and 5.62 in the right side. Basically 5% of observation can be left out or can be erroneous in nature. It can be biased, it can be flawed data, it can be not manipulated data, it can be anything, it can be an error, it can be an outlier also. But 5% of the data, if it contains flaws and drawbacks, it is still fine because you have 95% of chance your population mean will be between the lower limit and upper limit. Now let me explain this with some data. That way we will be able to understand this better. Let me open an Excel. This time let's take some random data and then try to see how confidence intervals help us achieve or perform this tasking operation in hypothesis. Now the first thing is we need a hypothetical situation. First of all, to know that we need some data for that. Maybe we can generate some data. First let's declare an hypothesis and then we'll create a data out of it, or the other way around. Okay, I'll say students and marks, school, from which school they're coming from. Let's create some data. Let's create 5 lines for each of the school. Yeah, now students are going to be addressed as a, okay, the students will be there as well. Or I would say instead of school, let's keep it section. That way it will be more relevant. So within a section, within a school, there might be multiple sections under each classes. So we are going to just take the help of that particular data and supply it into input. Now we have 11 items, so I'll just keep it as 10. That way we will have two elements, two sections. Each section will have 5 students. We will generate the marks randomly and we'll create an hypothesis. Now I'm going to have section A for the first 5 students, and the next 5 students will be section B. Yeah, that's all we need to do to create this data. Now let's create mark. I'm going to keep it in percentage. Yep, that's pretty much is what we need to do. I'll just convert things into percentage. Perfect. Now we have this actually is way too less. Instead of 0.65, let's keep 65 percentage. Perfect. So we have data here also. We will have 80.9. Okay, perfect. Looks like we have data points that are actually performing between 0 to 100 in the percentage of marks. This is purely the percentage of marks. This is the data that the school has. Okay, there are two sections in a particular class. Maybe let's consider SSLC. So the SSLC is a very important class for the school. So the school needs to focus on this particular class and identify what section is performing better and what section is performing poorer. Okay, in that case, now for them to know what, they need to have an hypothesis. The belief that they generally have is both the sections are performing better. So let me have a null hypothesis. The null hypothesis is basically the belief that we have. So the principal or some whosoever is saying the statement will have this particular statement, which is both the sections are performing better. Okay, let's talk about alternate hypothesis. Talking about alternate hypothesis, what we can have here is we can have a different statement wanted to evaluate whether they are different from each other. So what is it? Both the sections are not equal to each other. Whereas in null hypothesis, both the sections are performing equally. It's not better, it is equally. We can denote this as H O. H O is equal to H A. Basically, H naught is null hypothesis, or I'll say mean 1 is equal to mean 2. Then the second one is we have alternate hypothesis where it says m1 is not equal to m2. Mean 1 is not equal to m2, mean 2. This is the overall idea behind the hypothesis. Now, if I have to evaluate this, I assume I'm conducting an experiment. Conducting an experiment or asking the students to write the test, give a test to both the students, both the sections. I'm going to create a new set of tests. Set 1, set 2, set 3, set 4, set 5. Let's keep 5 set of tests for all the students in both the sections. Okay. Now there are 5 set of tests that we are going to give for each and every student from both the sections. In this case, the output might be very very close to what exactly there is in the data already, or we might have a new information as well. But what I'm going to do is I'm going to say section A scored so many, section B scored so many. Okay. We have only information for only one test. So what we can do is we can in this case also randomly generate the values. Let's randomly create this. In this case, I'll keep it percentage. Yeah, look at this. In this case, what happens is this is the average score. Let's understand this as average score. I'm just keeping all these numbers for our example. We will see it in a data set as well. Average marks. So average marks scored by students in section A in 5 different tests is this. If you see here, for the first test they have scored a very poor score. In second test they have performed fantastically well. The third test, fourth test they have performed poorly, and the fifth test also they did not perform well. Whereas if you see, section B has performed somewhere around 2 to 3 tests consistently compared to section A. Looks like section B is performing better than section A. But here the problem is, how confident am I about this statement? Now I've observed from the data that section B is performing better than section A. This is the understanding that I come to know after evaluating the students based on several tests, right? Now, how confident am I? How can I say 100% I'm sure? I cannot say 100% I'm sure, right? Because I've conducted the experiment only 5 times. Out of 5 times, see here, how many places B has performed better than A? Once, twice, thrice. Only 3 times section B has performed better than section A out of 5, which is basically somewhere around 3 divided by 5. So I'll say 3 divided by 5. 60 percentage. How confident am I? I am 60% confident that section B is performing better than section A. So when we generally quantify our confidence, what happens is we will always try to say, dude, I'm 100% confident that this will happen. 100% confident that India will win the match against West Indies or against Australia. You can be confident, but how can you quantify your confidence? Your confidence can be quantified by conducting the experiments, quantifiable experiments, n number of times. If I'm assume I'm doing this experiment like 10 times, let's do it for 10 times. Convert it into percentage. I'm randomly generating them, so I have no control over the data. Now I have conducted the experiment 10 times in both the sections. Now I have to see whether section B is greater than section A. How many times? Out of 10 times, I wanted to see how many times section B has performed greater than this. Looks like only 4 times section B has performed better than section A, whereas 6 times section A has performed better than section B. Right? So when I changed the data, things got changed. Okay, I think this is dynamic. Let me change this into static element. Now also we will have the same observations. Only 4 times we have section B outperforming section A, but 6 times section A is performing better than section B. Now my statement has to change, because if I keep conducting my experiment for n number of times, there are good chances that my assumptions will keep throwing me error. But ideally what we will do is, what we will consider is, if I'm conducting the experiment 100 times, I'll simply write 100 times the experiment is conducted, out of which 95 times I got the output that I want, that I assumed. 95 times accurate, or whatever I wanted to convey. If it is 95 times accurate, what happens? This becomes 95% true. 95% true. Whatever statement that I'm saying is 95% true, which is basically a confidence interval. Confidence interval is basically 1 minus whatever the percentage truth that you have. So 1 minus 0.95 will give me level of significance. Let me measure. Yeah. Yeah. If you look at this, I'm just going to convert this into percentage now. Only 5 percentage chances are there where you will have errors. Errors are wrong output, not wrong output, invalid or incorrect. So basically what happens is, you have an assumption, you already have an existing belief, which is null hypothesis. I am believing that India will win the match today, but someone else is saying no, India will not win, but I'm not sure whether the match will be a tie or a loss. Right, in that case what happens is, we will try to conduct the experiment n number of times, 100 times we will try to conduct the experiment, out of which 95% of chances, if there is a majority, 95% of the time, if it says India will win, and 5% of the cases it says no, India will not win, it will lose in 3% of cases, in 2% of cases the match will be a tie, then the majority is 95%, which is what we will consider as assumption. Then we will always stick with null hypothesis, which is simply nothing but India will win the match against Australia today. So the idea is simply conducting the experiment n number of times, out of which 95% of the chances at least, okay, we can also have 90% also, 90% true is also fine in real time, but 95 is the optimal confidence that you need to have. When I say 90% true, it means that out of 100 times, 90 times, even if your experiment gets successful, you can go ahead and finally say, yes, I found a new product after performing the experiment 100 times, where I have generated the desired output 90 times out of it, which is 90% of the cases. Even if it is 90% of the cases, if there are only 10% chances of errors, it is totally fine for you to go ahead and declare the product live. Or you can say claim the hypothesis. You can say reject the null hypothesis. Now start believing what I say, because this is proved by conducting the experiment several number of times. It should not be a fluke that output of an experiment is generated. There are good chances that it might be one chance output. So whenever we generate an output out of an experiment, if we have to validate it, we need to conduct the same experiment n number of times, out of which if 90 and above percentage of cases generate the same desired output, then you can go ahead and say I am 90% confident, I am 95% confident that this experiment will give me this result only, so we can believe this. It's all about quantifying the confidence in the output that you generated, or the new statement that you said. In our case, it is the new statement or the new belief saying that both the sections are not equal to each other. Looks like it is correct only because out of 110 times I did this experiment, 60% of the times section A is better than B. 40% of the cases section B is better than A. So in that case, there is no place where section A and B has performed really well. If section A performs better, section B does not perform better. If section B performs better, section A does not perform better. So it looks like both the sections are not equal to each other. We can believe this after conducting the experiment n number of times and going with the majority, which is section A is performing better than section B. This is the idea behind confidence interval. If you see here, it says 95% of your experiment should generate the same desired output, whereas if 5% of your experiment conducts or misbehaves in terms of generating output, see here, 2.5% in the right side of the distribution, 2.5% in the left side of the distribution. When I say right side and left side, it is basically from the mean, from the center left side, from the center right side. We can allow 2.5% error in the left side, 2.5% error in the right side, which can be outliers as well. This is the idea behind confidence interval. To simply reiterate one more time, confidence interval is simply nothing but an estimate which will quantify how confident are you with the output that you have generated. Have you done this experiment several times and have you achieved the output have you achieved the same output in the majority of the cases or not? Then if you are, if the answer is yes, then what is the majority? 90% chances or 95% chances? 99 or 100 is the best solution that we can achieve, but in real time achieving those numbers are not that easy. So 90 or 95 is literally amazing. Let's move on to the next topic. Level of significance. Confidence interval is how confident you are about the results. Level of significance is how much of a margin of error you wanted to allow inside your inside your what is this, inside the model or inside the prediction that we have to do. So the idea is when you have 90% confidence, then it becomes 10 percentage margin of error. The margin of error is something which is called as level of significance or alpha level. Let's theoretically see the probability of rejecting the null hypothesis if it is true. When I say if it is true, it basically becomes the right statement. If I have any right statements or right understanding, if I'm going to change the already existing belief with my new experiment, there might be not an 100% case where my new output will be the answer for all the cases. There might still be good places or few places where our old belief or our old logic might work. Now what is the percentage of chances that the old belief or the old output or the old logic will come into picture? Now to keep things very simple, I have let us take some data set this time. Let me create a new sheet. Here let's have our own hypothesis in this case. Now or I can say I can go with bath soap. Okay, in bath soap I am conducting some experiment. As a scientist, I'm conducting some experiment. My experiment results says that I've conducted this experiment once. At the end of it, it says 100% germs are killed. This is the output of my experiment. I'm identifying a new bath soap which will kill 100% of the germs in the body. Okay, this is the idea of bath. This is the output of my experiment, but I have conducted this experiment only once so far. What is the existing belief or existing fact? Existing fact is that 99.9% germs can be killed. But my experiment wants to have a new update to the existing belief, or wanted to say that no, all 100% of the germs can be killed using my bath soap. Now what I have to do is, this experiment has been done only once. Now what I have to do is, to prove my statement, to prove my claim, what I have to do is I have to do this experiment 100 times. Say for an example 100 times. So experiment conducting 100 experiments. Okay, out of which only 95 experiments are giving me the result of 95 experiments are giving me the result of 100% germs getting killed, but 5 experiment gives me somewhere greater than 99, but it is not 100, greater than 99, less than 100. Okay, this 5% chance is basically our level of significance. Level of significance is basically, this is actually the existing belief. What is the existing belief? The existing belief is a null hypothesis. Whereas I'm trying to change the existing belief with my alternative statement, hence it becomes alternate hypothesis. Now there are 5% chances where my experiments will return me the existing belief only, but however I'm going to go ahead and declare my soap as 100% germs killing bath soap. That way, when someone is using the soap 100 times, 5 times the germs may not be completely killed from his body. That is the idea behind level of significance. What is the percentage of error? What is the chances? What are the chances that the null hypothesis gets rejected even if it is true? Now, the above one that we are seeing here is confidence intervals. Ideally, in real time, we will always go with 95% and 5%. 95% you should be confident about the results. 5% you can have errors in your observations or in the output that you generate. Having 5% of error is not a big deal. It is acceptable because generating 100% clean output is not something very feasible to do in real time. So having 5% of error is totally fine in terms of conducting a new experiment, and still you can go ahead and claim, you can go ahead and reject a null hypothesis and then say my soap will kill 100% of germs in the body. This is the idea behind confidence level and level of significance. Theoretically, let's understand this. A level of significance, which is also denoted as alpha, is the probability of rejecting the null hypothesis when it is true. A significance level of 0.05 indicates a 5% risk of assuming that the difference exists when there is actually no difference. Exactly. So this control gap is our scope of error. 5% of chances I might wrongly predict the gender to be men when they are women actually. Whereas there are the same possibilities that I might predict someone as women when they are actually men. So this 5% error can be given a subsidy because it is really tough to generate or predict all the 100% of the information without having any errors. So the allotted margin of error is basically 5% only. This is the idea behind level of significance. Perfect. Let me delete this. Okay. P-value. Let's move on to the next one. P-value. P-value is basically nothing but probability value. When I say probability value, we will not be calculating this probability value. The machine automatically calculates the p-value for us, and we will simply use p-value to compare with the test statistic value that we will generate out of any hypothesis testing. Generally, we will do a lot of hypothesis testing: t-test, f-test, ANOVA, chi-square test, and f-test also. So when we do all this test, we will generate an output out of it through each and every statistics. So every test that I've said has a formula through which it actually takes the data and performs an operation out of it. The output, generated output, then will be compared with the p-value for that particular data set using degrees of freedom, which we will see in the next slide. So p-value is simply nothing but the probability of obtaining results at least as extreme as the observed results of a statistical hypothesis test, assuming that the null hypothesis is actually correct. Now, what is the maximum extent that this particular use case where we will have null hypothesis to be correct? We are going to reject null hypothesis if our confidence interval is 95% and we are going to accept alternate hypothesis. But in that case, what is the maximum extent? I'm sorry, what is the maximum extent in which we can actually consider null hypothesis to be true? Now the interpretation of p-value is simply nothing but if you have lesser p-value, it means that there is a strong evidence in the favor of alternate hypothesis. If you have a very minimal chances of occurrence of null hypothesis, it is actually good, right? Because you will have a very minimal occurrence of the existing belief. In most of the cases, you will have the current or updated belief or the fact. Hence, we can go ahead and reject null hypothesis. If the p-value is less than the statistic value, then we can go ahead and say reject the null hypothesis and say we can believe in the new observation. Whereas if we have the p-value greater than the statistic value that we generate out of any test, then we will say no, there is no good evidence that the new belief is correct. We will stick on to our existing belief, which is in case null hypothesis. Now let me explain everything with an example. I'm just taking a data set. Yeah, let's take this data set. Perfect. Let's take this. We will see ANOVA completely in a different class, but here I will try to explain you how we can take the help of different types of testing and how can we interpret p-value with the test statistic. Now I can show you these three, use this three data set, use these three columns to perform two different hypothesis testing. We can perform t-test also, we can perform ANOVA as well. So what I'll do is I'll just keep the entire three columns for ANOVA, whereas I'll keep only two for t-test. Now let's first do a t-test, before which we need to have our null hypothesis and alternate hypothesis. Null hypothesis. Null hypothesis is the existing belief. What is the existing belief? Mean value of both the groups are same. Okay. But someone is having a different idea. Someone is saying no, mean value of both the groups are not the same. Okay. Now we have data. Since we have not performed any analysis, we believe both the groups are same, but we need to conduct an experiment and validate it. To conduct this experiment, what I'm suggesting is, I'm saying no, not both the groups are same. There's a difference between each and every between the first group and the second group. In order for us to identify this, what we will do is we'll have to perform any type of t-test or a z-test or anything else, and validate the statement that we actually say in alternate hypothesis. In order to do it, what I'll do is I will first perform t-test in this case and then show you where does the confidence interval comes into picture, where the p-value comes into picture, and everything else with detailed example. For enabling data analysis, you have to go to data first, in which you will have data analysis tab. But you can, if it is not enabled in your machine, don't have to worry. Go to file, go to account, where settings, just looking for settings. Sorry, you have to choose file, and then I'll choose more. Let's see if options are coming here. Okay. Yes, if you choose options, you have to go to add-ins. In add-ins, what you have to do is you have to enable data analysis tool pack. You have to just go down. Yeah, here if you see, you will have data analysis Excel add-ins. If you just choose Excel add-ins and click go, you will have analysis tool pack and analysis VBA. Just give enable OK. they will be now part of your data tab. Now I already had it. So what I'll do is I'll simply choose data analysis tab, where we can perform all types of statistical testing without any issues. All these types of analysis can be done. Now what I'll do is I'll perform a t-test. Pad two sample for means and two sample assuming equal variances, unequal variances. There are different types here which we will see in hypothesis testing. In this case I'm going to go with the first type of t-test and supply the first group 1, and supply my second group 2. Then what are it has labels, basically it has columns. Look at this alpha level is basically the error margin that you can have. I wanted the output to be present in the same sheet, and then I just give okay. Now if you see here, it has given us the mean variance and what are the total number of observations present in each and every group, and what is the relationship between these two groups. 35% each group 1 is correlated to group 2. Mean difference is 0, and degree of freedom is 19. Degree of freedom we will see in the next slide. The idea is this is what we need to focus. T statistic. Just take this. Yeah. Now this is the statistic. This is called as statistics, which is simply nothing but the value that we were able to generate out of the given data set through the functions of t-test. So this is called as t statistics. Okay. Then what we need to check is what is the p-value for one-tail test and what is the p-value for two-tail test, because we do not know whether they are lesser than each other or greater than each other. Now if it is one-tail test, looks like p-value is greater than the, let me choose this. Look at this p-value, which is greater than the existing t-statistic value, saying that it has more evidence towards null hypothesis, which is mean values of both the groups are same. Now if I see it at a two-tail test, in two-tail test also my p-value is actually less than my actually greater than my t statistics. In both the cases, what we have to understand is my p-value is not less than the t statistics value, which means that it has more evidence towards rejecting alternate hypothesis and accepting the existing belief. What is the existing belief? That mean value of both the groups are same. So we will compare the p-value with the t-statistic value. This p-value is for one-tail test and this p-value is for two-tail test. We will talk about one-tail test and two-tail test in detail when we learn about hypothesis testing. But here the understanding is you compare the numbers with the t-statistic value. If the p-value is less than the t-statistic value, we will go ahead and reject null hypothesis. Other which ways we will reject alternate hypothesis and stick with the original one. Let me write the logic here. For one tail test, I'll say if this value is less than my test statistic value, tell me reject null hypothesis, or else accept null hypothesis. Yeah, in this case it says accept null hypothesis. Let me write the same logic here also. I'll simply copy this and change a few parameters. If J21 is less than J18, yeah, then we will say reject null accept null hypothesis. What does it say? It asks me to accept the null hypothesis. What is the null hypothesis? It says mean value of both the groups are same. Hence we can say that both the groups does not differ much. They are very similar in terms of value. They are not statistically significant from each other. This is the understanding that we will generate after performing several types of hypothesis testing with the help of both p-values and other components on it. Now we have degree of freedom. Degree of freedom is simply nothing but out of all the independent variables, how many variables can be independent can independently change. So basically, uh, yeah, if I have 20 independent variables here, if you see here, the number of observations we have is 20. If I have 20 observations, what is the idea is, if I wanted to interchange one variable with one variable in the place of other and replace the other with the other with the current place, I can do the interchanging and I can allow all the data points within my groups to change anywhere and you will still generate the same output. But the idea of degree of freedom is it should always be n minus 1, number of rows minus 1, number of columns minus 1. If you have two columns, it is always two column in minus 1, but in this case we are performing only on two columns where we have not asked the machine to take it as separate entities. So you don't have this c minus 1, you will have c minus 1 when we have more groups. I'll show this with an example using ANOVA, but the idea is n minus 1. If I have 20 independent variables, out of 20, 19 can be independent, one has to be dependent on the other. That is the idea behind degree of freedom as well. Let's see theoretically. Theoretically, degree of freedom refers to the maximum numbers of logically independent values, which are values that have freedom to vary in the entire data sample. As I told you, they can vary from one place to another place in terms of position, and you will still have the same output as we generated out of any particular statistical analysis output. Then they are discussed in relation to various forms of hypothesis testing in statistics, such as chi-square, t-test, and ANOVA. As I told you, yeah, as I told you, if I have only one variable, dependent from independent value, what happens is, look at this. My p-value actually is starts from 0 because the probability value is between 0 to 1, right? You will have very less correlation. But if I have more number of variables, the chances of having more cumulative statistic in terms of correlation as well as test statistics can be higher if I have more number of variables. And having all the variables independent of each other also helps the machine to understand the relationship between all these independent variables with the dependent variables. Let me show you with an example. Let's plot ANOVA this time. Yeah, now we have three groups. The idea of ANOVA is that whenever I wanted to compare the mean of three groups, I will use anything greater than 2, not just 3. Anything greater than 2 can be used with the help of ANOVA. Now let's have the null hypothesis. There are two null hypotheses in this case. That group 1 is same as group 2, or I will say group 1 is same as group 3, or we can say group 3 same as group 2. 1 with 2, 1 with 3. 3 is there, only 3 is not with 2. 2 is also with 1, and 2 is with 1, and 2 is with 3. Yes, yep, perfect. These are the three existing beliefs. To summarize it at a higher level, I'm saying mean values of all the groups are same. This is the entire idea of null hypothesis. Null hypothesis will compare group 1 with group 2, group 2 with group 3 with group 1, and vice versa. Now, what is my alternate hypothesis? Alternate hypothesis can be three different alternate hypotheses in general. I'll say not same as group 2. Not same as group 2. This is the idea behind null alternate hypothesis as well. So if null hypothesis is believing that everything is same, alternate hypothesis says no, the belief is wrong, there is some change in it, but it is not sure about it. As I told you, there can be three different forms of alternate hypothesis. I will say group 1 is greater than group 2. Here it says group 3 is greater than. This is one set of it apart from the one that we have written. Then the third piece of alternate hypothesis can be lesser than group 3. Yep, these are the three set of hypotheses. Here it says means are not equal to each other. Excuse me. I'll just paste this. Now here I'll change means are greater than each other. Here it will say means are lesser than each other. So there are three possibilities. Now the existing belief is that all the groups are same, but there are three possibilities that my existing belief can go wrong. What are the three possibilities? That the first one is they don't have to be equal to each other, and the second one can be the groups can be greater than each other. Excuse me, or it can be lesser than each other. So there are three different chances that my groups or my existing belief can change. Now in this case, yeah, let me plot ANOVA and compare and see how the groups are differing from each other, and then we will see what are the p-values, what is the ANOVA statistics, F statistics in this case, and compare the output out of it and see what are we going to accept and what are we going to reject. Now this is a one-way ANOVA. I'll just choose OK. This is my input range. They are grouped by columns, and I have labels in the first row. Alpha level is I can have 0.10 also, but as I told you, the optimal level of significance should be 0.05. I'm just going to keep it here. Just going to give it OK. That's all I have to do. Yeah. Now we have, let me open this. Now if you see here, this is my F statistic value and this is my P value and this is my F critical value. We will talk about critical value in a little while, but knowing P value and F statistic value helps us to decide on something. Now we will see what is our degree of freedom in this case. We have three groups. Look at what is the degree of freedom. Our degree of freedom is 3 minus 1, which is 2 between groups. Within groups there are 60 elements. There are three groups. So 60 minus 3 is 57 for us. So we have all these things. Look at this. The average of all three groups and the variance of all three groups. The average and variance for all three groups looks very close to each other. 20,000, 29,000, 26,000. There are good chances that the group A might be slightly different from group 2 and 3, but we are not sure about it. We'll have to quantify it with the help of the statistics only. Let me write my logic here. The logic is going to be if my p-value is less than the statistic value, then we will say reject null hypothesis. or accept null hypothesis. This is the idea. Yeah. If you see here, it says accept the null hypothesis. It says the mean value of all three groups are same. Not any of the groups, none of the groups are statistically significant from each other. So knowing this is very essential in terms of quantifying or in terms of understanding whether we need to go with the existing belief or also to validate if I have an existing belief. Now in this case, I had an existing belief that all three groups are same. Now with the help of small hypothesis testing, I was able to generate the logic out of it. Let's validate the degree of freedom also. Between groups, there are three groups. So as I told you, degree of freedom is always n minus 1. How many groups are there? Three groups. Minus 1 should give me 3 minus 1 should give me 2. Let me put this into a number. Okay, the number is 3 minus 1. It will give me 2. This is my degree of freedom. This is the total number of groups that we have. And elements within groups. There are 20 elements in each groups. There are 60 elements. How many groups are there? 3 groups are there. N minus G, which is 60 minus 3 gives me 57. So we have the same degree of freedom here, and this is the total degree of freedom, which is 57 plus 2, 59. And we have a statement also saying that p-value is greater than the f critical value, hence rejecting the alternate hypothesis and accepting the null hypothesis. So this is how we can go ahead and work on comparing groups and understanding whether they are significant, statistically significant from each other or not. This is the idea of degree of freedom. That brings us to the end of this class. Let me quickly recap what we have learned in the entire session. Now we started with understanding what is confidence interval. Confidence interval is basically nothing but the amount of confidence that you have in the output that you have generated. It is simply nothing but a metric that helps you to quantify the output that you generate out as an experiment. You can generate it as an experiment, or you can generate it as a assumption, or if you wanted to commit to a new theory, you can do it that as well. But you should make sure that the confidence interval is as big as it can be. The more the confidence interval is, the better it is. Then talking about the second idea, level of significance or alpha levels. Level of significance or alpha level is simply nothing but the margin of error that we will have in real time. If I'm conducting an experiment, there are good chances that my experiment will not give me the same output 100% of the times. Now, if we know that it will not give 100% of the times the same output, then what is the threshold that we can keep to to accept the margin of error? That is exactly what level of significance tells you. Level of significance or alpha level basically lets you choose your margin of error. If you have a particular margin of error, then it becomes easy for you to go ahead and then declare saying that, see, my output that I've generated out of an experiment is 95% accurate, 5% it will fail here and there. Talking about the second last thing, p-value. P-value is simply nothing but the probability value of the presence of null hypothesis being true in your data set. There are good chances, as I said, that the output that we are generating as an observation may not be 100% accurate. In that case, what we will do is we will try to generate output with minimal occurrences of null hypothesis being true. In that case, probability of p-value will tell us what is that particular percentage of occurrence of null hypothesis in the data set. So we can choose, and if I wanted to improve my p-value, I can add more data to it, or if I wanted to reject my alternate hypothesis, I can also do that with the help of understanding or comparing my p-value with the test statistic. Talking about degree of freedom, it is simply nothing but the proportionality in which the data is distributed in terms of columns as well as in terms of rows. It always takes one value as static and retains all the other values to be dynamically independent of each other, so that they can vary within the data set. How much they can vary? It is always n minus 1. If I'm working on only on groups at a column level, then it is number of columns minus 1. If I'm working it on both columns and rows, then I will take columns minus 1 plus rows minus 1. If I'm taking rows, I will make sure that if I have 60 line items in 3 different rows, if I have 60 line items across 3 different columns, then I have to minus the number of columns with my line items. That way we will have the total degree of freedom. That brings us to the end of this particular class. Thank you so much for joining this session. I hope you understood something out of this. Thank you so much. Please don't forget to like, share and subscribe to this YouTube channel. Thank you guys.